So, now we will do uniform acceleration. So, in uniform acceleration, as we have discussed its definition, so now here we can take its Vt graph. If you are taking a Vt graph, it is something like this. This side is your V, this side is T, that is a straight line. So, this angle is theta we can take. Here you can take any 2 point here like this. Suppose this is T1, T2, this is V1 and this is V2. And here we can take A, B, C, this is delta V and this is delta T. So, now see here, this is angle theta. We can write A is equal to delta V upon delta T. This we can refer as a average acceleration. But here, if you take delta T tends to 0, you will be getting A is equal to limit delta T tends to 0, delta V upon delta T is equal to dV upon dt. This is called instantaneous acceleration. But see here, in this case, since acceleration remains uniform, graph is a straight line velocity time graph. So, instantaneous acceleration as well as average acceleration both remains same throughout the motion. And we can also write here this is equal to, can be written also tan theta, that is called the slope. So, slope of the Vt graph is equal to tan theta, that is actually representing here acceleration. Now, one important point again with this, as we have done A is equal to dV upon dt, we can write d upon dt and dx upon dt, because velocity is the derivative of displacement with the time. Now, we can write A is equal to d square x upon dt square. So, acceleration can be written in this part, in this way. Now, see, it means acceleration is the second derivative of displacement with respect to time. So, we can also say the second derivative of displacement with the time is known as acceleration. Now, see another velocity time graph. If you have taken velocity time graph like this, here V and T, you are getting graph in this way. What does it mean? See here, the velocity is not changing with the time. In this case, slope is equal to 0. It means acceleration is equal to 0. It means body is moving with the constant speed. So, or constant velocity. So, when the body moves with the constant velocity, we call it, that is it has 0 acceleration. Now, by using this concept uniform acceleration and the theory of uniform acceleration, we will be deriving relations between the velocity time, position time and velocity displacement. So, we can go for the graphical method first. If you are taking here velocity time relation, for velocity time relation, I have taken graph like this is here, V and T here. Suppose the graph is like this. It means body is initially having initial at the 0 time having initial velocity u. It is not starting from the origin this graph, and the graph is a straight line, obviously acceleration is uniform. Now, this point is here the final velocity. Now, we join this point, we take it here, this is A, B, C and D. Now, we join over here and this total time here we can take here t and this angle is here theta. Just find its slope. What will be the slope of the graph? That is equal to here, this I have taken d, so this point I am taking as E. So, we can write A is equal to, that is the slope of the graph, velocity time graph, that is actually shows acceleration. We can write CE upon BE, and CE you can write V minus U divided by T, because 0 and this time is T. So, directly we can write here T, and then you can write or at is equal to v minus u, or you can write v is equal to u plus at. So, this relation is known as velocity time relation. So, by graphical method we can easily get velocity time relation, that is v is equal to u plus at. But in this process, in this formula, a remains constant with the time, that is the uniform acceleration, v is a final velocity, u is initial velocity. If body is starting from rest, initial velocity will be 0, and if the body is going to be at rest, final velocity will be 0. But in this graph here, when the body is starting, the initial velocity is not 0. So, now we will do other relations like a position time relation and the velocity displacement relation.